Hey guys, welcome to video 2 on Unit 3, and we are going to learn about Newton's second law of motion. Newton's second law of motion is written as a sentence that you probably aren't going to understand right now, but you will understand by the end of this lesson. It states the acceleration of an object depends directly upon the force of the object and inversely upon the object's mass. Let me just define those two terms, directly and inversely. So directly means that when one variable goes up, the other variable is going to go the same direction. When that same variable goes down, then the other variable will also go down. They move the same direction, okay? Inversely is opposite. Inversely means that when one variable goes up, the other variable goes down. When that same variable goes down, the other one goes up. So inversely means that the two variables move in opposite directions from each other, and directly means that the two variables move in the same direction as each other. So what this is saying is that acceleration will always go the same direction as the net force, and acceleration will always go the opposite direction as the object's mass. So for example, if the mass of the object gets bigger, acceleration is going to go the opposite direction. Acceleration will get smaller. And when your net force is bigger, your acceleration gets bigger. So let's prove that mathematically. So the formula for force, net force, which is very important, net force, it's capital F with lowercase net. Net force is equal to the mass of the object in kilograms, okay, that's our unit for mass, times acceleration. And acceleration, what are the units for acceleration? You should have this memorized from our previous unit. The answer is meters per second squared. So the force, your answer for force will always equal these two units times each other, which is why we call the unit of force a Newton. A Newton stands for 1 kilogram times meters per second squared. So if you have something that has 2 newtons of force, what you're really saying is that the force will move a 2 kilogram object, it will increase its speed, or it'll accelerate at 1 meter per second every single second. So that's what a Newton is. So let's use that formula. The net force equals mass times acceleration. This is very simple algebra work, so this should be very easy, okay? We're going to get to a lot more complicated stuff here in just a second. The net force is 10 newtons, and the mass is 2 kilograms. What's the acceleration? Remember, acceleration units are meters per second squared. First thing we do is we write out our formula, and then we're going to take the values that we know, and we're going to plug them into this formula. We know net force, that's 10 newtons, so I'm plugging it in for this spot, equals, we know the mass, it's 2 kilograms. We don't know the acceleration, so it's times acceleration. So to solve for acceleration, I need to isolate it, so I need to move the 2 kilograms to the other side. It's currently being multiplied by acceleration, so I have to do the opposite, I have to divide. So now I have 10 newtons divided by 2 kilograms will equal acceleration. So that would be 5, okay? And my units are meters per second squared. So 5 is my acceleration, okay? So now let's look what happens when I change my force. So my force here was at 10 newtons, but now it's at 20 newtons. I have multiplied my force by a factor of 2. My mass, however, is constant. I'm not changing my mass, okay? So when you don't change the mass, when the mass is the same, but you double your force, my question is, what's going to happen to your acceleration? Well, let's use our formula. 20 newtons of force equals 2 kilograms, that's the mass, times acceleration. Let's solve for acceleration, just like we did above. Okay. 20 divided by 2 is 10 meters per second squared. So my question is, when I doubled my force. It was at 10, it's at 20. I doubled it. What happened to my acceleration? Well, it was at 5, now it's at 10. Did it get doubled? Yes, it did. This tells me that acceleration and net force are directly related. Because when force is multiplied by a factor of 2, acceleration gets multiplied by a factor of 2 also. So force is getting bigger here, it's increasing. What is acceleration? It's also increasing. So a direct relationship. They move in the same direction. Okay, now let's look at what happens when I double my mass. So let's look at our first example. Our first example had an acceleration of 5 when the force was 10. So right here, I'm not changing my force. Okay, my force is constant here. And now my mass is being multiplied by a factor of 2. Okay, my mass is doubling. My mass is increasing. What's going to happen to my acceleration? Well, let's plug it into a formula. We have 10 newtons of force, like we did in the first problem. Our mass is now doubled from the first problem. Let's solve for acceleration. So I do the same thing that I did above, moving mass to the other side. 10 now divided by 4, my calculator gives me 2.5 meters per second squared. That's my acceleration. So what happened? Well, I had a mass of 2. I doubled it to a mass of 4. When mass increased by a factor of 2, what happened to my acceleration here? I had an acceleration of 5. Now I have an acceleration of 2.5. My acceleration decreased by a factor of 2. It got divided by 2. So this tells me that mass and acceleration are inversely related. Okay, they're inversely related because when mass goes up, acceleration goes down. Okay, so that is a quick, easy mathematical test to prove Newton's second law of motion. So, and then this next point here is just a reiteration of what we learned today in class. If the direction of the acceleration is known, the direction of net force is also known. Because if acceleration is moving, like let's look at this example. Here, the car is speeding up. Okay, we know that it's moving to the right. So velocity is to the right or positive. What does that mean about the acceleration? The acceleration is also moving to the right. It's positive because it's speeding up, right? When it's speeding up, your velocity and your acceleration should be the same direction. That means my net force is also going to be to the right because my acceleration direction and my force direction are the same. So whatever this diagram of the car is, here's the normal force of the car, here's the gravitational force of the car. Let's say maybe there's some friction here, but my net force, the applied force of the engine, is greater. It's speeding up in this direction. I know that this arrow is going to be greater because I know my acceleration's going to the right. So my bigger arrow is to the right. In this picture, the car is slowing down. Okay, what direction is the car moving? Well, the velocity is moving to the right direction, so it's still positive. But if it's slowing down, my acceleration has to be going the opposite direction. It's going negative. My acceleration is going negative. That means my force is also going to go the same direction, which is to the left. My net force. So here's your car. Here's your net force, your normal force, your gravitational force. Here's the engine. It's going forward, the applied force. Your friction force has to be a lot greater now because it's got to move, it's accelerating backward, it's slowing down. So that is just a reminder from our lesson on Tuesday. Okay, this next part is going to get a little bit messy. So it's really important that you watch this part slow. If I go over anything that you don't understand, you need to stop the video, you need to rewind, and you need to rewatch it. It's also really important that you take very thorough notes because what we're going to get into here is some hairy stuff. Okay, so if I give you a problem where I give you the mass of the object, okay, and I'm looking for acceleration, I say, hey, you with the hat, what's the acceleration of this guy? Okay, we're looking for acceleration. I give you mass, and I give you the amount of force that's being applied to the object. You can't use this formula. You might think at first glance, oh, here's my force, I'll plug it in here. Here's my mass, I'll plug it in here, and I'll solve for acceleration. But remember, what does this force here in this problem stand for? Does it stand for the applied force? No. It stands for net force. What is net force? Net force is when you add all your individual forces, I should have written that, all individual forces together. Okay? And you see what is the net force. So I only have one of the forces of this object. What are all the other forces acting on it? Well, this is where drawing free body diagrams comes into play. We practice this today with our free body diagrams scenarios. Here's an object. It's being pushed across the floor. It's being pushed. That means there's an applied force. And it gives us the value. It says it's 3.4 newtons. Okay, so 3.4 newtons is being pushed on this object. It's being pushed across the floor. That's a big hint. If it's being pushed across the floor, that means there's got to be friction going against the push, right? However, problem, I don't know the value of the friction, right? I don't know this value. Okay, I also know that since it's being on a floor, it's sitting on a floor, there's two other forces at play. There's the gravitational force, which I don't know the value of, and then there's the opposite of gravitational force, which is the normal force. And I don't know the value of that either. So here's my question. How can I add all the individual force vectors together if I don't know them? Well, you have to figure them out. So that's what I'm going to teach you. I'm going to teach you how to find these individual forces. Really all you need to find these individual forces is the mass of the object. Okay, mass is really important. The applied force is probably going to be given to you in a problem, but it's not always given to you. If it's not, you could always end up solving for it if you know your net force. But let's focus on gravity. Gravity is probably the easiest one to calculate, so we'll start there. This is the formula for calculating force due to gravity. That's what this stands for. Force due to gravity is the mass of the object times g. G is really A sub g. What is A sub g? A sub g is acceleration due to gravity. We learned this last unit. What is the value for acceleration due to gravity? It's negative 9.8 meters per second squared. Okay, that you'll need to memorize. So these formulas you don't have to memorize, but you do need to memorize the value for acceleration due to gravity. So let's calculate the gravitational force. Okay, the force of gravity is mass. What's the mass of this object? Well, it tells us right here. It says it's 3 kilograms. Here's the mass. It says times acceleration. What's acceleration? It's mass times g, I'm sorry. So g is the acceleration due to gravity, which is this value, negative 9.8 meters per second squared. So I'm going to put that in my calculator. 3 times negative 9.8. And I get negative 29.4 newtons. What does that negative stand for? Hopefully you said it stands for the downward direction. So the gravitational force, you can write it as a positive number because we're already showing the negative with this downward arrow, if that makes sense. So my next question now is, how do I find the normal force? Well, if you remember what we talked about today in class, Gravity pulls on objects downward. If an object is sitting on an object, like if an object's sitting on a floor or a table, but it's not falling through the floor or the table, what does that mean? Well, if an object is not accelerating downward, that means the normal force and the gravitational force are, you guessed it, they're balanced. So the gravitational force and the normal force will always be the same value. They're just going to be different directions. Gravity is going to pull this object down 29.4 newtons, but the floor that the object's resting on is going to push it up 29.4 newtons in the other direction. So if you wanted a formula for that, I could do it like this. Here's the gravitational force. Think of it being downward. Here's the normal force. Think of it being upward. Same exact value, just different directions. Okay. The only time this is not true is when your object is not sitting on a floor or a desk or a table. If it's like being thrown, for example, it's not sitting on anything, then you don't have a normal force, okay? You still have gravitational force. You'll always have gravitational force. But you won't have a normal force if the object is like flying, for example. Okay, so we have found gravitational force and we found normal force. The next thing we need to do is find our friction force. Okay, this one's just a tad more complicated. Here is your formula for finding friction force. F of friction just means the force of friction. This weird little symbol, it's a U with a teardrop. Okay, this U with a teardrop, I'm actually going to write it over here so I have more room. The friction force is this guy. It's pronounced mu. That's how it's pronounced. This is called mu. And mu stands for the coefficient of friction. The coefficient of friction is a value that usually goes from 0 to 0.9. It's like a constant. It's a frictional constant that exists for every single object that you're sliding something on. The bigger the number, so like 0.9 would be a bigger value, the bigger the number of the coefficient of friction, the rougher the surface is, the greater the friction is on that surface. For example, if I have a ball and I'm rolling it on the table, the coefficient between the ball and the table is going to be really, really low because there's not a lot of friction there. However, if I have sandpaper, okay, and then I have some tennis shoes, and I want to roll the tennis shoe, I want to push the tennis shoe along the sandpaper, that's going to have a really high coefficient of friction because there's a lot of rough surface there. So higher numbers mean more friction. This is a value that I will give you in a problem, or I'll ask you to solve for in a problem, okay? And then it's going to be multiplied by, you can see down here, it says the normal force. So whatever your normal force was, it's going to be multiplied by that. So let's try that. Let's find our coefficient of friction. I'm going to give you the coefficient of friction. I'm going to give you mu. Okay, let's say, since it's being pushed across the floor, let's give it 0.4. Okay, that's the mu I'm giving you. And then you have to multiply it times normal force. What's our normal force? Well, we calculate it to be 29.4. So we do 0.4 times 29.4. And we get our friction force is 11.76. And that probably was too high because I did not practice these numbers. I made up the coefficient of friction, and it doesn't really go with my example because now the net force is going this direction towards the friction. Step you need to do is you need to draw the free body diagram of what's happening. So ignore numbers right now. I just want you to write down all the forces that are happening. Here it says an applied force is used to accelerate an object to the right. So the applied force is to the right. So here's my free body diagram. I drew an arrow that shows my applied force right here. And it's across a frictional surface. That means there's friction. Friction is going to be moving the opposite direction of my push. So here's the force of friction. And then that's it. It says neglect air resistance. Well, if it's being pushed across a floor off a, well, it doesn't say floor, it says surface. So if my object's being pushed on a surface, we know that there's a normal force at play. And of course, we obviously know that there's the force of gravity. So that's what you need to do first. Label all your forces, and then I want you to go back and add a magnitude to your forces. So you're going to go back to this problem and you're going to look and say, okay, the applied force was 20 newtons. So I'm going to come back here and write down 20 newtons for my applied force. And then do that with any other force you see. So here there's 10 newtons of friction, so I labeled it right here, 10 newtons of friction. Okay. And this problem doesn't say it, but it's supposed to say that the gravitational force is 100 newtons. I don't know why I forgot to type it, but it's supposed to say that. So here's my three forces, okay, right here. Then, after you do that, I want you to label everything the question's asking you for. So this says use the diagram to determine the normal force. So we're looking for normal force, which is why I put a blank here, okay? I forgot to write down step 3. Label what you're looking for. Okay, and then we want to find the net force. So I write that down here. By the way, the mass, the acceleration, and the net force of the object, always label them down here underneath your free body diagram. You're looking for the coefficient of friction. Always put your coefficient of friction over here because I just want it to be next to your frictional force. And then it wants to know the mass of the object and the acceleration of the object. So here I've just went ahead and boxed everything we're looking for. Now, this is really important. Every single physics problem you're going to be answering in a different way. So don't get comfortable with how the order in which I'm answering this problem, because every problem that you solve, you're going to probably have to use different formulas and figure out different ways to solve for it. So this type of problem is all about doing critical thinking and problem solving. So what I would do is I would just go through in no particular order each thing you're looking for and ask yourself, can I solve for this? What's the formula for this, and do I have everything for it? So let's start with the normal force. Here's the normal force. How do I calculate normal force? Well, this is something that you should know from our previous problem. The formula for normal force is the gravitational force, right? It's just in a different direction. So here's the formula for normal force. Now you have to ask yourself this question. Do I have everything for it? So here's the questions you're asking. A, what's the formula? And B, do I have everything in that formula? And if you know the question A, if you know the formula, and you have everything in that formula, then just go ahead and solve it. Do we have the gravitational force? Yes, we do. It's 100 newtons downward, right? And another way to say it is it's negative 100 newtons. So what's our normal force? Well, we know that the normal force, according to our formula, is in the opposite direction of your gravitational force. So it's 100 newtons upward. Well, that one was pretty easy. Now let's look and ask ourselves another thing. It can just be random. You can just pick anything on here. Let's pick mu. We want to find mu. What's the formula for mu? Well, there's not really a formula just for mu, but there is a formula that has mu in it. Do you remember this formula? The force of friction is equal to mu times your normal force. So could you rearrange this to solve for the coefficient of friction? Sure. Let's go and do that. I'm assuming you know how to rearrange equations since we practiced that last unit. If you don't, I'll kind of quickly explain. I just divided both sides by the normal force right here, got rid of it, and I divided it on this side. So it's the force of friction divided by the normal force. So now ask yourself question B. Do you have everything in this formula? Do we have the force of friction? Yes, we do. It's 10 newtons. That's handy. Let's put that right here, 10 newtons. Do we have the normal force? Well, we sure do. We just calculated it. It's 100 newtons. So I can find mu, or my coefficient of friction. It's 10 divided by 100. And so once you do that, you get 0.1. So mu is 0.1, 0.1. So I'm going to go ahead and put that right here. Now let's look at mass. See, I'm just going through in a random order. I'm asking myself these questions. I'm trying to do them in different colors so you can see. Mass. Is there a formula for mass? No. But there is a formula that has mass in it. It's this formula. The net force equals mass times acceleration. Okay. Do we know the net force? Nope, we don't. Do we know acceleration? Nope, we don't. So that's probably not a good formula to use, okay? However, there is another formula that has mass in it. I don't know if you remember, but it's the one that the gravitational force is mass times gravity's constant. So let's ask ourselves, do we have these things? We do have the gravitational force, yes. We do know G, it's always negative 9.8. So can I solve for mass? I sure can. So mass is going to be my gravitational force divided by gravity. What's my gravitational force? It's 100 newtons. What's gravity? It's negative 9.8 meters per second squared. Okay, this is important. Since gravity is negative 9.8, it's going downward, you also need to include your negative here. The force of gravity is downward negative 100 newtons. So if you do 100, divide it by 9.8, you get 10.2. And remember, mass is always in kilograms. So here's my mass. So what you should see what I'm doing is I'm looking for formulas that have everything in that. If you find that a formula does not help you out, for example, this one was not helpful for us because we didn't have net force and we didn't have acceleration. So I crossed it off. Sometimes you can find another formula that can help you out, but if you get to a point where you can't find a formula that can help you out, just leave this one blank and come back to it later. A lot of times you'll find the things you need later on in your problem. Okay, what I want to do now is solve for my next unknown, which is acceleration. So, okay, I'm going to have to reuse green here. Acceleration. Is there a formula for acceleration? There sure is. Acceleration is final velocity minus initial velocity divided by change in time. Do we have any of those things in this problem? No. So this is not a helpful formula. Is there another formula that might have acceleration in it? Yes. The one that we X'd out earlier. Net force is mass times acceleration. I could rearrange to solve for acceleration if I have everything. What do I have? I have mass because I found it, but do I have net force? I don't. So this is an example where I found a formula I could use, but I still don't have everything for it. So I'm going to leave acceleration blank. I'm going to come back to it later. Now let's look at net force. Here's my net force. Okay. What's my formula for net force? Well, it's the same formula. But what's my problem? I have mass, I don't have acceleration, so that formula is not helpful. But there is another way you can find net force. Do you remember? To find net force, you can add together all your individual forces. Add all individual forces. So let's look at our diagram. We have all our individual forces, right? The normal force and the gravitational force look like this. Here's the normal force. Subtract it from your gravitational force. There's no net force in the upward or downward direction. Okay, no net force there. Let's look from side to side. Well, there's 10 newtons to the left and there's 20 newtons to the right. So 20 newtons to the right minus 10 newtons to the left gives me 10 newtons to the right direction, in the rightward direction. That is my net force. Yay, so I have net force. That's awesome. It's 10 newtons. Now, let's go back and see, was there anything we weren't able to solve? Well, remember how we weren't able to solve acceleration? Let's go back. We were looking for net force, we didn't have it. Did we get it? Yes. So now I can solve for acceleration. What's my net force? 10 newtons. What's my mass? I actually forgot. Oh yeah, it's 10.2 kilograms. What's my acceleration? Well, I just need to rearrange my formula to solve for acceleration. So it's 10 divided by 10.2, and my acceleration is 0.98 meters per second squared. Make sure your acceleration is the correct sign. I'm going to double check. It says the object is moving to the right, and it's speeding up to the right. So if it's moving to the right and it's speeding up, then the acceleration should be to the right. So it should be in a positive direction, and it is. So I did it correctly. That is an example of a force problem. You have to take your time. You have to do all of the steps. If you miss the steps, then you're going to struggle with the problem. So I'm not actually going to do this last one with you since we have met our time limit. So on your practice problems right here, you have to solve one similar to the one I solved. And actually, there's two problems I want you to solve. And you need to try. And you need to go back and try the steps that I walked you through. Okay, so if I hear that, oh, I tried, but I had no idea what I was doing, you need to go through each of your steps, okay, so that you can solve this problem. All right, that's it for today. I will see you guys Thursday.